Good afternoon, everyone. Wanted to talk about joint work with a couple of co-authors here at Budish, economist at the University of Chicago, Andy Lewis-Pye, mathematician at London School of Economics. As most of you know, I'm head of research at EC'24, what I'm here in my academic capacity. Needless to say, nothing in this talk should be construed as financial advice. So economic limits of permissionless consensus. And first tell you about what I mean by consensus, and I'll tell you what's permissionless part, and I'll tell you where the economics comes in. First, the picture I want you to have in your mind, what is the blockchain protocol? There's software that allows a whole bunch of physical machines, like these on the left, maybe scattered all over the earth, communicating over the internet. Software that allows a bunch of physical machines to collectively simulate the state of a single virtual machine, which I'm picturing on the right. So when I talk about the computer in the sky, I'm talking about this virtual machine on the right. Why would you want to bother to do this? Well, a bunch of reasons, but like, just for example, any of these physical machines over here, it has an owner, someone who can just flip a switch and turn it off. Okay? Whereas ideally, if this is a large set of nodes scattered all over the place and you have a well-designed blockchain protocol, this computer should be very hard to turn off. Okay, no one has any access to this computer. Turning it off should be as hard as, in some sense, stopping, turning off the internet. And so if you think about sort of the internet, it's kind of like global infrastructure for communication. The point of a blockchain protocol, like say Ethereum, is to provide global infrastructure for general purpose computation. Okay. So consensus, so keeping a bunch of physical machines in sync on some common state, classic problem, dates back to the 1980s. Couple Turing Awards were given away, sort of awarded to the pioneers in this area. The minimal requirements you want of a consensus protocol, first of all, liveness. So as long as there's stuff that's got to get done, it should get done. So if there's transactions to process, the protocol should process them. And the other thing you always want is consistency, right? So if at some point a transaction is regarded as confirmed, you want it to be regarded as confirmed forevermore. It should never be rolled back. Whenever I say a consistency violation, I mean that something went wrong and actually the protocol wound up rolling back a transaction that's thought to be confirmed. Okay, so if you heard like a double spend attack, that would involve a consistency violation. Why is consensus not trivial? Well, classically, there's sort of two challenges that one focuses on. First of all, some of the nodes running the protocol, they do so incorrectly. Okay, maybe just because there's sort of bugs, or maybe there's sort of a hostile actor who's actually trying to mess up your protocol. Okay, so presumably, if 100% of the nodes are correct, maybe this is an easy problem. If all of the nodes are controlled by some adversary, presumably you can't do anything. And basically, the foremost obsession classically, at least to people who wrote the protocol, is identifying the threshold where consensus flips from possible to impossible. So to identify the maximum fraction of faulty nodes such that you can still provably maintain both consistency and liveness. So challenge number one, faulty nodes. Challenge number two is the communication network, like say the internet, maybe less reliable than you, so maybe unpredictable. The delays that are suffered by messages en route to their destination. Okay. Now, starting with Bitcoin, people started thinking about permissionless consensus, which is sort of the consensus problem, but a harder version, where you want to design a protocol that literally has no idea who's even running it. And so Bitcoin has that property. It's really remarkable. Before that came out, I doubt anyone would have thought it was even possible. That shows it's possible. In general permissionless consensus, you have to address multiple challenges in addition to the classical ones. So for example, it may be the case that someone tries to join your protocol under multiple different identifiers. And so that's why every permissionless consensus protocol has a civil resistance component, like proof of work in Bitcoin or proof of stake in Ethereum and many other modern blockchain protocols. And another thing that's important for us today is that you may want to have a consensus protocol that sort of accommodates fluctuating participation among the non-faulty participants. So like if you're running some Bitcoin machines, you're doing Bitcoin mining, maybe you go away for the weekend, turn off your machines, and you come back. Bitcoin actually will operate just fine with honest players coming and going, as long as 51% of the participation is honest at any given moment in time. So that would be a still harder version of permissionless consensus where you accommodate the honest players coming and going. Okay? So what this paper is about, it says, well, suppose someone tries to attack one of these blockchain protocols. So to basically take control of a lot of those physical machines, so many of the physical machines that you actually could create a consistency violation if you wanted to. And we want to ask the question, is there anything that consensus protocol could do to fight that? Okay. For example, to ensure that such an attack would be economically costly for the attacker. Okay, we want to understand whether or not that's a property that these protocols can have. The promise for having this kind of punishment of an attacker has always sort of rested with blockchain protocols that use proof of stake civil resistance, right? And you sort of see why. It's a proof of work protocol like Bitcoin, where sort of the power of participant depends on like how many computers they own. What is this poor piece of software like supposed to do, right? It can't reach out an imaginary arm and like turn off their computers. Whereas if the sort of participation stems instead from something controlled by the protocol itself, like native cryptocurrency, stake, locked up in a smart contract that this blockchain protocol sort of maintains, all of a sudden it's conceivable the protocol could, in a programmatic way, actually punish anyone who tries to attack, who tries to cause a consistency violation. Okay? And so that's been the hope for like literally 2014, we started thinking of discussing what's possible benefit of proof of stake protocols. And Ethereum famously switched from proof of work to proof of stake a little less than 2 years ago. If you look at there's other proof of stake protocols as well that have this idea that Ethereum is easily the biggest one. And if you look at their official documentations, they basically kind of assert that this is true. They say, why did we switch to proof of stake 2 years ago? It's because it makes these kinds of attacks, these takeover attacks, more costly than they were in Ethereum's original proof of work implementation. Okay. Now, I'm a theoretician. I like to do foundations. So I see kind of an assertion like this, and I'm like, is this like true? What does that even mean? Okay. Is it like a theorem? Does it map to a theorem in a plausible mathematical model? But actually, it's not just the theorems are missing, even like the definitions are missing. Like, what does it even mean for like one protocol to be more economically secure than another? Like, how would you prove or falsify that statement? And so the point of this paper is to, for the first time, introduce a mathematical framework where these kinds of questions can be rigorously interrogated. Okay. So the paper has 3 results. I'll tell you a little bit about all of them. 2 of them are going to be negative results, so impossibility results. That say we can't get the kinds of protocols that we want. That's going to be under 2 different sets of somewhat weak, incomparable assumptions. We can't get what we want in those 2 cases. Then we'll make a stronger set of assumptions and we'll have a possibility result, positive result. We can get the kinds of protocols that we want. Obviously, to say any of those theorems, they have to say what is it we want. Okay, so that's sort of a new definition in this paper. So we introduced the idea of the EAC property. And EAC here stands for expensive to attack in the absence of collapse, meaning the absence of a collapse in the cryptocurrency price. Old arguments about why people wouldn't want to take over a blockchain protocol relied on sort of a crash in the cryptocurrency price. We would like a protocol that can fight back even in the absence of any kind of price collapse. So what does the EAC property say? The idea is to capture asymmetric punishment of an attacker. An attacker, again, I mean someone who perpetrates a consistency violation, rollback of transactions. So we would like to be the case that anyone who causes a consistency violation is guaranteed to be punished, to lose resources. But meanwhile, anyone who honestly follows the protocol, no matter what else happens, is guaranteed to not lose resources. Asymmetric punishment of an attack. Okay. So getting this right formally actually takes a fair bit of work. So there's a fair amount of economic modeling in the paper, which you should check out if you want to see the details. For this talk, this is definitely sort of sufficient intuitive understanding. Attacker guaranteed to lose resources, like for example, stake. Honest player is guaranteed to not lose resources. Okay? Can a protocol have this property? Okay. So like I said, 3 results, first 2 negative results, saying that under certain sets of incomparable assumptions, you cannot get the EAC property. And then there's going to be a positive one. You're not supposed to know what all the words on the slide mean. It's just to kind of give you a big picture that you can slot the results into as we go through it. So the assumptions here are weakest at the top and strongest at the bottom. So the point of this paper is really just to identify this horizontal dotted line, which is the threshold where you move from unattainable, where EAC is unattainable, to where it is attainable. Okay. So let me talk through the left part of the diamond, the right part of the diamond, and then the bottom part of the diamond. Okay, so again, incomparable sets of assumptions here, stronger assumptions on the bottom. Okay. All right, so let's start with the negative results. You can't have the EAC property. Well, actually, that's not quite going to be the statement of the negative results, because in some regimes, you're going to have the EAC property in a vacuous way. Okay? So in particular, the regimes where classical consensus is always lived, where the adversary controls a small enough fraction of the resources that you can guarantee consistency and liveness. Well, if you're in that regime, you can't have a consistency violation. There's nothing to punish. You will be EAC just by default. So the format then of a negative result will be that as soon as the attacker is large enough, controls a large enough fraction of the resources, that they're in a position to carry out a consistency violation, at that exact moment, they will also be powerful enough to evade any attempt at asymmetric punishment. Okay, that is what a negative result looks like for this property. And that is the statement of these first two results. Okay. All right. So for the first negative result, we're going to make our life easy in one way and difficult in a different way. We're going to make our lives easy by assuming a very reliable, we're going to assume the internet's having a good day, okay, which is called the synchronous model. So every message just gets delivered within some known time, like say 5 seconds. Okay, so no worries about long delays. We're going to make our lives difficult by insisting that, like, for example, Bitcoin, it works even in what's known as the dynamically available setting, which just means we want honest players to be able to turn their machines off over the weekend and come back. Okay? We want it to work as long as at any given moment in time, the active participation, is a sufficiently large amount of honest players. Okay? And so we will have an impossibility result for EAC. Okay? If in this regime, because we're in the synchronous model, it turns out, okay, that if an attacker controls less than half of the resources, even for example, only 49% of the hash rate in Bitcoin, if you design your protocol properly, there will be no consistency violations. You are going to be EAC just vacuously. But this theorem says that as soon as you have 50% of whatever the protocol is, 50% of the hash rate, 50% of the stake, 50% of the resources, whatever they may be, at that point, you cannot guarantee asymmetric punishment against this attacker. So pictorially, if you think about parameterizing by the adversary size, over here, the adversary doesn't exist, 100% honest. Over here, the attacker controls everything, very simple picture. 2 regimes. This is where you just have classical security, consistency violations impossible, so trivially EAC. Again, the magic threshold between the 2 regimes in this case is 1 path. To the right of that, at the first moment, consistency violations become possible. You cannot actually punish them asymmetrically. So that's the first negative result. Second negative result, same kind of conclusion under incomparable assumptions. We've learned our lesson in theorem 1. We can't be dynamically available. We can't let people turn their machines off over the weekend. So here we're going to make the stronger assumption, which is known as the quasi-permissionless setting. And this just says that whoever the protocol is counting on to participate, like to cast votes to create a quorum certificate or something like that, whoever the protocol is counting on to be active and online, let's assume they are in fact active and online. Okay. So that's the quasi-permissionless setting. That makes our life easier. On the other hand, we're going to assume that the internet might be having a bad day. Okay. So we're going to assume that there are periods of finite but possibly unknown duration where we don't have control over the message delay. So in other words, we're thinking about it in a day where we might be under a denial of service attack. Okay? That's known as the partially synchronous setting. And here again, it is the case that you cannot be non-trivially EAC. Okay, so equally simple picture, 2 regimes. The regime on the left, which is where consensus 1 classically lives, no consistency violations, trivially EAC, and then the regime where it's big enough to cause consistency violations, and again, here no asymmetric punishment is possible. Now, insult to injury, actually, for this negative result, you can't even punish the adversary, the attacker, allowing for collateral damage to the honest players. Okay, so it actually turns out that they can just cause a consistency violation and run away, get away with murder before you can do anything about it. Okay. So that's the story here. So that's the left part of the lattice, the left corner of the lattice, and the right corner of the lattice, respectively. Theorem 3 at the bottom, part of the diamond. We say, okay, we learned our lessons from the 2 impossibility results. We can't let honest players turn off their machines over the weekend. We got to work with the quasi-permissionless model. We're counting on people to vote. Let's assume for the analysis they do indeed vote. And we can't allow arbitrary message delays. We can't allow just so far arbitrary denial of service attacks. We're going to work in the synchronous setting, have it down with message delays. And here you can have non-trivially protocols. Meaning that you have attackers that are so large that you do not have security in the classical sense. It's so large, meaning more than 1/3 of the resources, where they can actually cause consistency violations. But as long as they're less than 2/3 of the resources, like 66% of the stake or less, then you can guarantee asymmetric punishment. You can guarantee that attack would be extremely economically costly for the attacker while leaving all of the honest participants unharmed. The 2/3 threshold here is tight. Okay, once an attacker controls 2/3 of the resources of a protocol, they in effect have unilateral control of the protocol. There's nothing. Okay. So for this third result, we have 3 regimes. Again, the one that historically has been the one studied, classical security, no consistency violations. And then you have sort of the case where the attacker has unilateral control. This is new. This is the first time we've had a regime that's provably like this. You do not have security in the classical sense, but you do have it in this sort of economic sense. In the sense that all attacks are possible, they're guaranteed to be costly. Just to recap the results, picture. Let me leave you with some implications for practice, because actually there's a lot of lessons in these theorems, both for kind of, ex post facto sort of justifying design decisions that have been made in Ethereum and other protocols, and also guidance for protocols to be designed in the future. So theorem 1, right, that was about sort of protocols that can accommodate honest players coming and going. One implication of that is that if you want asymmetric punishment, you can't do proof of work. Okay? So Bitcoin's not going to work, nor the proof of work protocols can work either. You have to switch to proof of stake or something else like it. Implication number 2 is that even if you switch to proof of stake, you're not going to be able to do it with a typical longest chain protocol. Reason being, longest chain protocols are typically meant to work in the dynamically available setting. So this is interesting because Ethereum, when they switched to their new protocol a little less than 2 years ago, the 2 biggest aspects of the switch were the switch to proof of stake and the addition of a finality gadget, okay, to do these periodic checkpoints. And so what this first theorem says is neither one of those changes would have been sufficient in isolation. The only way to get provable sort of slashing properties, provable punishment, is to make both of those changes at the same time, which is what they did a little less than 2 years ago. Second theorem was the one that kind of said if you have unbounded message delays, you can't get the EAC property. More generally, we talk about this in the paper. It shows that even in the synchronous model, like whatever your loose bound is, and how long it takes people to communicate, right? So for example, maybe you suppose that even in a denial of service attack, if you're running the Ethereum protocol, you can still use social media to communicate within like a day or 2. Maybe that's your sort of like bound on sort of message delay in the synchronous model, theorem 3. Then you actually need the cooldown period. The cooldown period means here if you're a staker, and you sort of indicate your intent to unstake. The cooldown period is how long it takes after you express your intent to actually get your assets back. The cooldown period actually needs to scale with the amount of time it takes people to communicate while under attack. And that is, in fact, for Ethereum and many other proof of stake protocols, indeed sort of the heuristic by which cooldown periods have been chosen thus far. And this shows that that's provably necessary. You really cannot have shorter ones. The takeaway for the third result, I think, is the obvious one. For a decade, the vision has been to use proof of stake protocols, slashing to have asymmetric punishment. And for the first time, we have a mathematical proof that as long as you design your protocol properly, you can, in fact, attain that goal. Thanks very much.